The big difference between the ideas of Aristotle and those of Galileo and Newton is that Aristotle believed in a preferred state of rest, which any body would take up if it were not driven by some force or impulse. In particular, he thought that the Earth was at rest, but it follows from Newton's laws that there is no unique standard of rest. Both Aristotle and Newton believed in absolute time. That is, they believed that one could unambiguously measure the interval of time between two events, and that this time would be the same whoever measured it, provided they used a good clock. Time was completely separate from and independent of space. This is what most people would take to be the common-sense view. However, we have had to change our ideas about space and time. Although our apparently common-sense notions work well when dealing with things like apples or planets that travel comparatively slowly, they don't work at all for things moving at or near the speed of light. The fact that light travels at a finite but very high speed was first discovered in 1676 by the Danish astronomer. He observed that the times at which the moons of Jupiter appeared to pass behind Jupiter were not evenly spaced, as one would expect if the moons went round Jupiter at a constant rate. As the Earth and Jupiter orbit around the Sun, the distance between them varies. He noticed that eclipses of Jupiter's moons appeared later the farther we were from Jupiter. He argued that this was because the light from the moons took longer to reach us when we were farther away. His measurements of the variations in the distance of the Earth from Jupiter were, however, not very accurate, and so his value for the speed of light was 140,000 miles per second, compared to the modern value of 186,000 miles per second. Nevertheless, his achievement in not only proving that light travels at a finite speed, but also in measuring that speed, was remarkable, coming as it did 11 years before Newton's publication of Principia Mathematica. A proper theory of the propagation of light didn't come until 1865, when the British physicist James Clerk Maxwell succeeded in unifying the partial theories that up to then had been used to describe the forces of electricity and magnetism. Maxwell's equations predicted that there could be wave-like disturbances in the combined electromagnetic field, and that these would travel at a fixed speed, like ripples on a pond. If the wavelength of these waves is a meter or more, they are what we now call radio waves. Shorter wavelengths are known as microwaves or infrared. Visible light has a wavelength of between only 40 and 80 millionths of a centimeter. Even shorter wavelengths are known as ultraviolet, X-rays, and gamma rays. Maxwell's theory predicted that radio or light waves should travel at a certain fixed speed. But Newton's theory had got rid of the idea of absolute rest. So if light was supposed to travel at a fixed speed, one would have to say what that fixed speed was to be measured relative to. It was therefore suggested that there was a substance called the ether that was present everywhere, even in empty space. Light waves should travel through the ether as sound waves travel through air, and their speed should therefore be relative to the ether. Different observers, moving relative to the ether, would see light coming toward them at different speeds, but light's speed relative to the ether would remain fixed. In particular, as the Earth was moving through the ether on its orbit round the Sun, the speed of light measured in the direction of the Earth's motion through the ether should be higher than the speed of light at right angles to that motion. In 1887, Albert Michelson and Edward Morley carried out a very careful experiment at the Case School of Applied Science in Cleveland. They compared the speed of light in the direction of the Earth's motion with that at right angles to the Earth's motion. To their great surprise, they found they were exactly the same. Between 1887 and 1905, there were several attempts, most notably by the Dutch physicist Hendrik Lorentz, to explain the result of the Michelson-Morley experiment in terms of objects contracting and clocks slowing down when they moved through the ether. However, in a famous paper in 1905, a hitherto unknown clerk in the Swiss Patent Office, Albert Einstein, pointed out that the whole idea of an ether was unnecessary. Providing one was willing to abandon the idea of absolute time. A similar point was made a few weeks later by a leading French mathematician, Henri Poincaré. Einstein's arguments were closer to physics than those of Poincaré, who regarded this problem as mathematical. Einstein is usually given the credit for the new theory, but Poincaré is remembered by having his name attached to an important part of it. The fundamental postulate of the theory of relativity, as it was called, was that the laws of science should be the same for all freely moving observers, no matter what their speed. This was true for Newton's laws of motion, but now the idea was extended to include Maxwell's theory and the speed of light. All observers should measure the same speed of light, no matter how fast they are moving. This simple idea has some remarkable consequences. Perhaps the best known are the equivalence of mass and energy, summed up in Einstein's famous equation E is equal to mc squared, and the law that nothing may travel faster than the speed of light. Because of the equivalence of energy and mass, the energy which an object has due to its motion will add to its mass. In other words, it will make it harder to increase its speed. This effect is only really significant for objects moving at speeds close to the speed of light. For example, at 10% of the speed of light, an object's mass is only 0.5% more than normal, while at 90% of the speed of light, it would be more than twice its normal mass. As an object approaches the speed of light, its mass rises ever more quickly, so it takes more and more energy to speed it up further. It can in fact never reach the speed of light, because by then its mass would have become infinite. And by the equivalence of mass and energy, it would have taken an infinite amount of energy to get it there. For this reason, any normal object is forever confined by relativity to move at speeds slower than the speed of light. Only light or other waves that have no intrinsic mass can move at the speed of light. An equally remarkable consequence of relativity is the way it has revolutionized our ideas of space and time. In Newton's theory, if a pulse of light is sent from one place to another, different observers would agree on the time that the journey took, since time is absolute, but will not always agree on how far the light traveled, since space is not absolute. Since the speed of the light is just the distance it has traveled divided by the time it has taken, different observers would measure different speeds for the light. In relativity, on the other hand, all observers must agree on how fast light travels. They still, however, do not agree on the distance the light has traveled, so they must therefore now also disagree over the time it has taken. In other words, the theory of relativity put an end to the idea of absolute time. Before 1915, space and time were thought of as a fixed arena in which events took place, but which was not affected by what happened in it. This was true even of the special theory of relativity. Bodies moved, forces attracted and repelled, but time and space simply continued, unaffected. It was natural to think that space and time went on forever. The situation, however, is quite different in the general theory of relativity. Space and time are now dynamic quantities. When a body moves or a force acts, it affects the curvature of space and time. And in turn, the structure of space-time affects the way in which bodies move and forces act. Space and time not only affect, but also are affected by everything that happens in the universe. Just as one cannot talk about events in the universe without the notions of space and time, So in general relativity, it became meaningless to talk about space and time outside the limits of the universe. In the following decades, this new understanding of space and time was to revolutionize our view of the universe. The old idea of an essentially unchanging universe that could have existed and could continue to exist forever was replaced by the notion of a dynamic, expanding universe that seemed to have begun a finite time ago and that might end at a finite time in the future.